Hello, I'm Charlie Thompson, and welcome to the pre-lab video for Lab 1, Latitude, Longitude, and Time Zones. This is just a diagram showing some sizes, some lengths on Earth. The equatorial circumference, if you were to measure Earth at the equator, it's 40,075 kilometers. If you were to measure Earth going from the North Pole to the equator to the South Pole and back up to the North Pole, that's only 40,008 kilometers. Earth is kind of bulgy at the equator because it used to be more molten, and as it spun, it got all bulged out. So it's actually shortest if you measured through the poles. It's longest through the equator. We are one of 3 countries that doesn't use the metric system. The United States, Liberia, and Myanmar are the only 3 countries that don't use the metric system, which means in this class we'll have to use both. The whole scientific community uses the metric system. Americans don't. In 247 BC, Eratosthenes of Alexandria calculated the circumference of Earth within a couple percentage points. Amazing, amazing math. In the notes for this lab, I'll put a link to the video by Carl Sagan where he talks you through how Eratosthenes was able to do this just using shadows at noon, and walking off the distance between Alexandria and Syene. Amazing story. So, Earth's locations and time zones. The whole point of latitude and longitude is to make a grid, and the whole point of that grid is so that we know where places are. So that, for example, you can go back to them. You know where you are, you know where other things are. That's the whole point of the geographic grid. There are lines of latitude. They are called parallels because they're all parallel. They run east and west, but we use them to measure north and south. And then there's lines of longitude. The lines of longitude are used to measure how far west or east from the prime meridian you are. So the lines of longitude run north-south, but we use them to measure west-east. The lines of latitude run east-west, and we use them to measure north and south. So let's go through latitude for starters. Latitude is the degrees that something is either north or south of the equator. If it's on the equator, there's no angle, so the latitude is 0. Lines of latitude are called parallels because they're parallel. The equator is the longest line of latitude, and as you get away from the equator, the other parallels get smaller and smaller and smaller until you get to the North Pole, which is just a dot. So the 90th parallel north is, in fact, a dot. So now we've got a diagram. If you were to measure from the equator a 49-degree angle and then mark it, and then measure another 49-degree angle over here, and then connect all of those dots, you would end up drawing what is the 49th parallel. So the line that you would make by connecting all the dots that are 49 degrees north, that's the 49th parallel. The equator is 0 degrees, the North Pole is 90 degrees north, the South Pole is 90 degrees south. You can see the equator is the longest line of latitude, and by the time you get to 60 degrees north, that parallel is half the circumference of the equator. The equator is about 40,000 kilometers around, and the 60th parallel is about 20,000 kilometers. So lines of latitude, they run east-west, but we use them to measure north and south. They go from 0 degrees at the equator up to 90 degrees at the North Pole, 90 degrees at the South Pole. I might as well tell you, our latitude is about 40 degrees north. Longitude is the measurement east. It's the number of degrees. So again, it's an angle. We're measuring an angle east or west of the prime meridian. Meridians are the lines of longitude, and those are lines connecting all points along the same longitude. Those are called meridians, and they're all the same length. So if we were to draw an angle 60 degrees east of the equator, and then connect all the points that are 60 degrees east of the prime meridian, that would be the 60th meridian, 60 degrees east, 30 degrees west. As you can see, all the meridians are the same length. It goes from 0 degrees to 30 to 40, 60, up to 180 degrees. And then from the other side, 0, 30, 60, up to 180. So the equator, 0 degrees, 15, 30, 45, 60, up to 180 degrees. And then same thing in the eastern hemisphere, 0, up to 180 degrees east. And I've written east and west. That's just so you know what hemisphere we're looking at. If you're giving the longitude of what is the international dateline at 180 degrees, you don't need to see east or west. It's both. It's neither. The prime meridian and the international dateline, 180 and 0. You don't need to say east or west. And when you're giving longitude, it works the same way. You just need to give the direction. So you could say this is 180 degrees west. You don't need to say 180 degrees west longitude. That's redundant. So time zones are a function of longitude. Well, I'll keep talking about this, but Earth rotates 360 degrees in one day. That works out to 15 degrees in 1 hour. So the Earth has been divided up into 24 time zones, each of which is 15 degrees wide, because that's how far Earth rotates in 1 hour. In fact, it was this awareness that Earth rotates through 360 degrees in one day that allowed the first way of finding our longitude. And that was by using this clock. John Harrison was a clockmaker, and he developed a clock that was accurate enough to be brought on board a ship. In fact, you needed 2 clocks. You needed 2 clocks to figure out your longitude. One of them you kept on your home port time, and the other one you kept on your local time. So the local time, every day at noon, you would adjust to noon. The home port stayed whatever it was. You're sailing along. Your local time is 1 p.m. Your home port time is noon, so you're 1 hour away, so you're 15 degrees away. Because it's later where you are, you know that you are east. So that would, if your home port time says noon and your local time is 1 hour later, 1 p.m., that means that you're 15 degrees east. So we put latitude, longitude together to make the geographic grid. I would say the location of this red dot is 48 degrees north, 60 degrees east. When you give a coordinate pair, it's always latitude followed by longitude. So always, 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 it's latitude first and then longitude. So the equator and the prime meridian intersect at 0 degrees. I'm laughing at the voices in my head because oftentimes there's an imaginary place called Null Island, and it's 0 degrees, 0 degrees. And I used to teach computer mapping, GIS systems for American River College. And when you grab a data set from someplace, if they didn't do a good job of configuring the input, you're going to get a lot of garbage data. Like if people don't know their latitude and longitude, and so the form records it as 0 degrees, 0 degrees, suddenly all of your users are going to get plotted. Their location is going to show up in the middle of the Atlantic Ocean, just off the coast of Africa. And so geographers have it's an inside joke that the location of all of these bad data points is called Null Island, 0 degrees north, 0 degrees, well, there's no north, south, east, west because it's the equator, it's the prime meridian, but Null Island is 0 north or 0, 0. So this is the geographic grid. This is a 15-degree grid, so I just made red lines every 15 degrees of latitude. So that'd be the equator, 15, 30, 45, 60, 75, 90. And then same thing for longitude, 0, 15, 30, 45, 60, 75, 90 degrees west, 105, 120 degrees west. So if you were to give our latitude and longitude to the nearest 10 degrees, you'd be 40 degrees north, 120 degrees west. Here they are with labels. There are a couple important lines of latitude. There are a couple important parallels. The equator at 0 degrees. The tropics, the Tropic of Cancer in the northern hemisphere, the Tropic of Capricorn in the southern hemisphere, represent as far north and south as direct sunlight is going to hit during the year. So in March, the sun's over the equator. June, on the June solstice, it's over the Tropic of Cancer. The September equinox, it's over the equator. The December solstice, it's over the Tropic of Capricorn. And then next March, it's back up to the equator. Above the Arctic Circle and south of the Antarctic Circle, those represent the locations that have 24 hours of daylight in the summertime and 24 hours of night in the winter. So at the equator, every single day is 12 hours long. And if you're at the North Pole, well, if you're at the North Pole, over the course of a year, you'd have the sun coming up for 6 months, and then the sun would be below the horizon for 6 months. And on the summer solstice, in fact, for a bunch of days around the summer solstice, you would experience 24 hours of daylight, which is great until it comes time for December, in which case you have a whole bunch of days with 24 hours of pitch black darkness day after day until the sun comes back up. So those are some of the key parallels that you need to know. And if you look on a photo or satellite imagery of Earth, you can see that these parallels are pretty important. For example, the equator, right around the equator, it's where the world's rainforests are. So Indonesia, Africa, the Amazon, right under the Tropic of Capricorn, Cancer here, and Capricorn, that's where the world's great deserts are. So South Africa, most of Australia's desert, the Atacama, which is widely known as the driest place in the world. There's a weather station there that went 14 years without recording any rain. The American Southwest, the Sahara, Saudi Arabia. So the world's deserts are pretty much right under the tropics, right under the tropics. In lecture, I'll make a big deal out of some of the zones of latitude and what those actual latitudes are. Equatorial going from 23.5 south to 23.5 north. The subtropics, right below the tropics. The mid-latitudes, where we live. Subarctic, right below the Arctic. And then above the Arctic Circle is the Arctic. Below the Antarctic Circle is the Antarctic. Diagram from the book. You don't need to know this for lab, but it's important because the latitudinal zones have totally different weather, totally different climate. So latitude, I'm just going to tell you this throughout the entire semester. I've been teaching geography for 20 years, and here's what I've learned. 95% of everything we will talk about in physical geography can be explained from latitude. And if it's not latitude, it's plate tectonics. So here we have ultraviolet light coming in over the course of a year, and you can see there's a very clear latitudinal pattern going from the equator. And as you get away from the equator, there's just less ultraviolet light over the course of a year. I just said 95% of everything is latitude, and if you can't explain it via latitude, it's plate tectonics. So this pink area with higher ultraviolet light, this pink area here with higher ultraviolet light, that's caused by high elevation, caused by mountain ranges, caused by plate tectonics. So because these places are higher, the atmosphere is thinner, and less of the ultraviolet light is filtered out before it hits the ground, so there's higher amounts of ultraviolet light. Ultraviolet light, it turns out, is necessary for us to be healthy. Our skin needs to be exposed to ultraviolet light in order to manufacture or synthesize vitamin D. Nowadays, we get it through processed foods, but back before the 1950s or so, people living at higher latitudes, for example, in the former Soviet Union in the winter, because they would have had really short day length, they actually would bus children south so that they could get hours of daylight, so that they would get vitamin D. One of the big obvious effects of this is human skin color. Because ultraviolet light is very powerful, it breaks apart DNA. So the regions of the world with the highest amounts of ultraviolet light are the regions of the world where the people that have been living there longest have darker skin tone. You can see higher latitudes have lighter skin tone. Because they're getting less light, too much melanin that would protect them from ultraviolet light would block the ultraviolet light, and they wouldn't get enough vitamin D. If you don't have enough melanin to protect your skin, then you're in more danger of skin cancer in these regions. So skin color is just a function of latitude because ultraviolet light is just a function of latitude. So, time zones. There are 24 time zones. They are 15 degrees wide. Well, theoretically, they're 15 degrees wide. In reality, they get broken up and they zigzag so that you don't split a state, so that just part of the state would be an hour off. The international date line zigzags to avoid splitting countries, like it should run through this part of Russia. So if the international date line really was just the 180th meridian, right here, this part of Alaska, it would be Monday, and on the other side, it would be Tuesday. It'd be 7 o'clock in the morning Monday, 7 o'clock in the morning Tuesday. So the international date line zigzags around the island nation of Kiribati so that they didn't have to cut that up into 2 days because that would be confusing. There's a couple places that have weird time zones. I'm not going to ask you about weird time zones on the test. They're half an hour off, 15 minutes off. So here we've got earlier times, midnight, 1, 2, 3, 4, 5, 6, 7, later. So as you move eastwards, it's later. In Los Angeles, if it's Pacific, we're in the Pacific time zone, so Los Angeles, San Francisco, Sacramento, Pacific time. If it was at 11 o'clock in the morning, it would be 1, 2, 3 hours later in New York. It would be 2 hours later in Chicago, 1 hour later in Denver. As you go east, it's later because that's the way Earth spins. Earth rotates from west to east. So some other, here's another time zone map. This is, I believe, the CIA's time zone map. You can see across the ocean, the lines are nice and straight, but then as the time zones move over land, they move around, like I said, to avoid splitting up states. I think this is a really good diagram. You can see how far off from Greenwich you are. So here's 0 hours. This is Greenwich. 1 hour behind, 2 hours behind. So if it was midnight, it would be 11 o'clock, 10 o'clock, 9 o'clock, 8 o'clock, 7 o'clock, 6, 5, 4 o'clock in the morning. So you could just take the time in Greenwich, it would be midnight, and subtract 8. Here are the time zones for the US. We are in the Pacific time zone, 8 hours off of Greenwich, 7 hours off, 6 hours off, 5 hours off. And each time zone is centered on a central meridian. So our time zone, the defining meridian, and the meridians, you can see they run down, they split the middle of each time zone. So that each time zone is 15 degrees wide. So this time zone, the central meridian at 1:35, 7.5 degrees on one side, 7.5 degrees on the other. So each time zone is 15 degrees wide and centered on the controlling meridian. So the controlling meridian, wow, it's not even Monday. The controlling meridian for the Pacific time zone is 120 degrees west. The controlling meridian for Central Time is 90 west. The controlling meridian for Central Time is 75 degrees west. On the other side of the world from the prime meridian is the international date line, where today becomes tomorrow. So over here it's Sunday, over here it's Monday. So it's entirely possible you could take off Monday from New Zealand and land in Hawaii Sunday. You could take off Sunday and land Monday. You could take off Monday and land Sunday. Really weird. So about time zones, I've gone over this, but I think it's important to go over things until everybody understands it. Earth rotates through 360 degrees in 24 hours, which works out to 15 degrees each hour. So if it was noon in Greenwich, it would be 1 o'clock in the time zone next to it, 2, 3, 4. On the other side of the world is the international date line. If it's 6 o'clock in the morning here, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock. Earlier in the west, later in the east. And that's it. I wish you good luck on your lab. If you have questions on anything, please email me, please text me, please call me. I'll set up a Zoom meeting. I'll call you back. We'll text, whatever it takes for you to figure it out. And good luck.